Hey guys, today we are going to be analyzing scenarios. It's kind of putting these two things together, and then these are the last notes before we have a test, okay? 'Cause it's not a whole lot of information. So we're doing this on page 9, which means since it's an odd number, it will be on our right-hand side of the page. We're leaving page 8 blank, and you will see why in class. Okay, so we're on page 9 now. We are analyzing scenarios. Your notes for this might be on Tuesday, 9/22. It also could be on a different date, so write the date of your next class. And the learning target is I can determine the types of data and domain and range based on a given scenario. Now, this doesn't look long, but when we say types of data, that means that we can identify independent and dependent variables, and we can identify if it's discrete or continuous, and then we can do things based on that knowledge, okay? So it's kind of taking the 2 days of notes and like wrapping it all together. So what we're gonna do is, they're less like notes and more like worked examples, so we're gonna do 2 different scenarios, and then we will extend that in class. Okay, here is scenario 1. So scenario 1 is that pizzas cost $8 each. Gavin and his friends ordered pizzas and want to give a $5 tip to the delivery person. The total cost per number of pizza is shown in the table. Okay, so here's my table. So the right-hand column is, the left-hand column is the number of pizzas, and I have 1 through 5 and then a dot, dot, dot. And then the right-hand column is total cost, and that's blank right now. And then you can see some other things here, so if you want to pause this and write this down, you can. But I have IV for independent variable, dependent variable, dependency statement, and then domain and range. Okay, so we're going to start on the table. So for the table, I just want to show you that these numbers that we're going to fill in here aren't actually magic, okay? It's based on the scenario. So each pizza costs $8, and no matter what, they want to give a $5 tip to the delivery person. So that means the total cost for one pizza would be $8 plus $5 for the tip. So that's $13. Okay? So then 2 pizzas would be 2 times 8, which is 16, and then the $5 tip makes 21. Okay, and again, if the math is fast, I just want you to know that it's not magic. This is how we're getting these, okay? 3 pizzas at $8 each would be 3 times 8 is 24, plus 5 more is 29. 4 pizzas at $8 each is 4 times 8, which is 32, plus 5 more is 37. And then 5 pizzas for $8, that's 5 times 8 is 40, plus 5 more is 45. Okay, so I could have had those filled in, but I want you to know that it's not random. It's based on coordinated with the scenario. And then you'll notice I have a dot, 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 and that's because there isn't really a maximum number of pizzas right now that they can buy, so I'm just giving a little ellipse here because in the scenario, they could order more than 5. I don't know what they're going to order. All right, so now that we have this filled out, we can talk about the type of data it is. So, based on our information, we know that since we're ordering number of pizzas, you cannot order parts of pizzas. Okay, that means that these are counted items. Okay, and since they're counted items, that means that this data has to be discrete. I can't connect the dots because it doesn't make sense to have halves or quarters of pizza. Maybe when you're eating it, but not when you're ordering it. So that makes this all discrete. Okay, and that's something that you're going to want to determine before you do domain and range and before we do our graph in a bit here. Now we want to do it before domain and range because that determines that we're going to use roster notation instead of an inequality. So roster notation, remember we do D colon for domain is, and then a curly bracket to represent a set. And roster notation is literally just a list. So you can order 1 pizza, or 2, or 3, or 4, or 5, and then remember we added ellipses to say, oh, and it continues in this fashion. So it can go 6, 7, 8, so on. Okay. Now the range, we're going to go ahead and give us a curly bracket there. So R is the range. And again, even though you can do money in between these, like you can, you know, hypothetically spend $20, which is in between 13 and 21. The problem is that because we can only order certain numbers of pizza, and that's all the scenario talks about, we have to stick to these numbers. Because if you walked up to them and said, here's $20, what can I get? Well, that's not an option here. Okay, so we need to just list these numbers. So again, we have 13, 21, 29, 37, 45, and again, ... it continues in this fashion. And if you were to look at what's happening here, we're actually adding by 8 each time. So if you wanted to continue the list, you just have to add 8 to the number each time. Okay? Great. So now we have that we know that it's discrete, and we have the domain and the range. Now we want to talk about independent and dependent variables. So again, in this scenario, we have that one of these that controls the other is the number of pizzas you order. The number of pizzas you order is going to affect how much they're going to charge you, or your total bill or total cost. Now, I know you might think, well, what if you only have a certain number of money? What's that? Oh my gosh. What that is called is a restriction, or a restraint on this. That just means that your domain can't go as high. If you only had $50, then this would stop here and it wouldn't go any higher. But it doesn't turn this into the independent variable, okay? It still is affected by how many pizzas you choose to order. So you just need to be careful. But having a table is super helpful, because we know that the X column, which is always to the left, represents our independent variable. So that must be the number of pizzas ordered. Sorry, I have been doing so well. These, again, are cursive Z's. I normally write them that way, but I tried to do it the other way for you. And then that means the Y column over here is our dependent variable, which is always the second one. So it's either to the right or it's below if it's horizontal. So that is the total cost. Okay, and then DS I have for dependency statement, and so a dependency statement, remember, is always in the form of the dependent variable depends on the independent variable. So we say that the total cost, that's my dependent variable, depends on, and you always use that phrasing, depends on, and then I'm just going to bring it down to the next row, the number of pizzas, there we go, ordered. Okay, so there's your dependency statement. So you'll notice that I was color coordinating this whole time. Everything that has to do with independent variable, domain, X value, those are all tied together. So I made those all pink. And then Y values, dependent variable, range, those are all tied together. So I made them all blue. Okay? So now what we're going to do is over here I'm going to set up a graph, and we're going to graph it. Okay. So now I have my graph, my X and Y axis set up, and I'm actually going to add X here and Y here. Okay, so it's just in quadrant 1 because it's positive, positive, but that's what we want to graph. And if you want to pause and draw that, you can. But now what I'm going to do is label the axes. So remember, the independent variable always goes on the x-axis, which is horizontal. So that means down here, I'm going to label this as number of pizzas. And then we want to do the y-axis, or the vertical axis, as the dependent variable, which is total cost. So, sorry, I got to rotate the paper a little bit, but this is the total cost. And because I know that it's in dollars, I'm going to put in parentheses a little dollar sign to be my units. I don't have number of pizzas because the unit is pizza, so you don't need to do anything there. Okay, so now what we want to do is scale the axes so that it incorporates this. Okay, so the good news is if we have to go above 5, that's okay, because you technically could extend the table if you want to, but we need to make sure we get to at least 5. So that's going to be 0, and if I just go 1, 2, 3, 4, 5, that's only like halfway, so I don't want to do that. I believe that I want to skip every other, so that this one is 1, 2, 3, 4, and 5. Ooh, that's perfect. Okay, there you go. So it's nice and spaced out. Remember, each gap needs to be exactly the same. I went up by 1s, and each one has 2 squares in between. Okay, then here I need to get up to at least 45. If I go by 5s, I don't think I'm going to get up high enough. 5, 10, 15, 20, 25, 30, 35, 40, 45 right here. That's not bad, but let's see what happens if I go by 4s instead of 5s. 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44, 48. Ooh, that looks good. We'll be like just right at about 45 here. So let's go by 4s. So again, you don't have to label every single line if you don't want to, but you need to make sure that it's consistent. So every 1 square represents 4. So from 0 to 4 is 4. From 4 to 8 is 4. From 8 to 12 is 4. So it needs to be consistent. So we're going to go up by 4s till we get to the end. Okay. So this one where the arrow is 48, but I'm not actually going to mark that. But actually, I was able to squeeze all the numbers in, so that's good. All right. So the next thing we want to do is actually plot my pizza points. So we go 1, and the price is 13. So I'm going to go to 12, and I'm just going to go like a little above that, and that's my 13. Okay? Because there's a gap of 4 there. So you don't want to go quite halfway. Halfway would be 14. So I went like a quarter of the way up. And then 2 will be $21. So I'm going to go up to 20 and then just a little bit above 20. Okay? Kind of see where this is going. And then 3 is 29, so I'm going to go up to 28. Ooh, I kind of did a good job here, guys. Go a little above that. Go 4 pizzas, and that's 37, so I'm going to go 36 and go a little above that. And lastly, number 5, we're going to go here and go up to 44, and this will be just 1 above that. There we go. Ooh, it looks like a nice little straight line. Perfect. So that's it. Now I know that we have these ellipses here. You don't add that on a graph. A graph you have to take as a snapshot. The graph continues, but this is cut off and this is cut off, but there's arrows indicating that we could extend it if we wanted to. And then in addition to that, you need to think through this last step, that the first thing we did was decide that this is discrete. And since it's discrete, we do not connect the dots, because even though you can pay in decimals for money, you cannot order numbers of pizzas that are decimals. So we don't connect. I'm going to do like a little speech bubble like I did before. Don't connect discrete data. Give it a little speech bubble so we know that that's just like a little comment. Okay? And there you go. So now we've done a whole scenario. We have a table for it. We analyzed if it's discrete or continuous, and based on that, found the domain and range using appropriate notation. We found the independent and dependent variables and wrote a dependency statement, and then we graphed it using, again, independent and dependent variables, and then our knowledge of it being discrete to know whether or not to connect the dots. Okay? So that is the whole analyzing that you will do, and we're going to do one more example. All right, here is scenario 2. Scenario 2 says that the table shows data from Jenna's recent softball drill. It shows the time after releasing the ball straight up in the air and its height from the ground. So we have time elapsed, which means from when she releases the ball, it's the time that has passed since that exact moment. And we have some decimals, but it's in seconds, and you think about it, that's probably happens really fast, right? The ball goes up and comes down, and it's not very long. And it looks bad, but then when we think about it, it actually is taken at equivalent intervals. So here we go up by 0.3. If you add another 0.3, you get to 0.6. If you add another 0.3, you get to 0.9. If you add another 0.3, you get to 1.2, and if you add another one, you get 1.5. So it's actually nice because those are already split into even intervals. Then we have the height of the ball in feet from the ground. And it kind of looks weird because it starts at 6, but then if you think about it, she doesn't like have her hand on the ground and like throws it up from there. It doesn't start on the ground. She probably has her arm extended above her head, and when she releases it, it's at 6 feet in the air. Okay, and then when she catches it, it's at the same height. Okay, obviously this is a made-up scenario, but there you go. And again, you'll see some similar notes here: independent variable, dependent variable, dependency statement, domain, and range. Okay, so again, the very first thing we want to do is determine what type of data this is. Well, since time is something that is measured with some sort of tool like a stopwatch or a clock, okay, and same thing with height, some sort of tool like a tape measure or a ruler, right? So since both of these are measured, that makes this continuous data. And again, we want to determine that before we go and make a graph and before we try and do our domain and range. So for domain and range, we need to know that because it determines what type of notation we'll use. So since this is continuous, we're going to use inequality notation because it's not just a set of numbers, it's like a range, and it can be anything in that range. So I again am color coordinating, but I switched the dependent to green because I thought the blue was a little bit too light. But here we go. When we do inequalities, again, we start with a curly bracket, but then we want to find the lowest number. So the lowest number in the dependent, or x's, is 0. So that means we're going to start with 0 here. And again, since there's no like open circles and no graph, we just default to our less than or equal to sign. We use an x because the domain is a description of the x values, and then again our normal sign because we only change that when there's an open circle on a graph, or we use plus or minus infinity. Okay, and then we have to find the highest value in the x column, which is 1.5. So we're going to take that and put it here. Now, I chose this example specifically because I wanted you guys to be aware that it's not always the lowest numbers the first one and the highest numbers the last one or something. You might actually have to hunt for them. So we start with our curly bracket, and then we want to find the lowest value. Well, the lowest value occurs twice, but it doesn't matter because it's 6. So you can say it's that 6 or that 6. It doesn't matter. It's always the same number. And then, again, our less than or equal to sign, and then y, because the range is y values, and then less than or equal to, and now we have to find the highest number. And again, the highest number is there, so we'll put 15. Okay, so here it's saying that our x values fall in this range and our y values fall in that range. Okay, now, we want to identify the independent and dependent variables. So the independent variable is always the first one, or the x column, and that is our elapsed time. And then our dependent variable is always our y value, or our left or second column, which is the height of the ball. And I mean, again, you can get as specific as you want. Remember, this is the elapsed time since she released the ball, and this is the height of the ball from the ground. So, I mean, we can get really fancy when we write our dependency statement if we want to. But we just want to make sure that we get them in the right order. So remember, it goes, the dependent variable depends on the independent variable. So our dependency statement is that the height of the ball depends on the elapsed time. Okay, and don't like try and confuse yourself. It's not like, oh, because time is passing, the ball always has to get further and further and further away. This is a particular relationship called a quadratic relationship, so it makes sense that it actually goes away and then comes back, but all of this is dependent on the time that's passed. Okay, so just trust the table and the data, right? Okay, so the last thing we want to do is graph this information. So I'm going to set up a graph. All right, so here we have our graph set up, or the axes, and again, we want to label them X and Y. And then we want to actually give labels to the axes based on this particular scenario. So the independent variable always goes on the x-axis, which is down here, and that is the elapsed time. And again, I now know the units, which is seconds. So I want to make sure to include the units if I have them. And then over here is the height of the ball. I'm going to have to rotate just so that I can actually write that, but the height of ball, and that is in feet. All right, excellent. Now what we want to do is, again, scale so that we are able to fit this on our graph, but not just fit it in like a little corner so that it takes up most of the graph so that we can actually see what's happening. Whoopsie daisies, I'm so sorry. So again, this is 0, and I only have to go out to 1.5. So what I want to do is, remember, these are spaced evenly already, so I could just go 0.3, 0.6, 0.9, 1.2, 1.5. But again, that's only going to take me about halfway, so instead I'm going to label every other. So I'm going to do a space of 2 squares, and that's going to be 0.3. 2 more squares will be 0.6, 0.9, 1.2, and 1.5. Okay? And the reason, again, this works is because the distance from 0 to 0.3 is 0.3, and I use 2 squares. The distance from 0.3 to 0.6 is 0.3 with 2 squares. So each of these are spaced evenly, and the distance between the numbers is spaced evenly. Okay? If the distance between the numbers was like 12 and the other ones weren't, then that would look wonky. You don't want to do that. Okay, now here, remember, my lowest is 6 and my highest was 15. So I want to make sure I get up to at least 15. And I can't go by ones, and I feel like 5s, 5, 10, 15, that's not going to be good. Let's see what happens if I go by 2s. 2, 4, 6, 8, 10, 12, 14, 16. Okay, so that gets me here. Again, I still have a big chunk here. So I can't go by ones and I can't go by 2s. So I want to get a little creative. What if every 2 squares was a distance of 3? So 2 squares is 3, 2 more squares, 6, 2 more squares, 9, 2 more squares would be 12, 15, and that top line would be 18. Okay, so that made it spread out a little bit more. Again, if you wouldn't think to do that, you could have done it with 2s. It would just be a little short. Okay, so here you go. There's your scale. The next part is to then graph it. Now we gotta be careful because the first number is 0, which means it's literally on this line, right? Because you haven't gone over in the x direction at all. It's 0. And we want to go up to 6 feet. There you go. And then when we do 0.3, we want to go up to 11. So I'm going to go up to 12 and then back down like a little bit to make 11. 0.6 is going to be 15. Ooh, that was good because I picked a number where we got 15. 0.9 is also 15. 1.2 is 11 again. So I'm going to go up to 12 and then back down to 11. And then 1.5 is 6 again. Okay. So now I have my dots, but because this is continuous, I need to connect this. Now, I don't want to just do straight lines because it's going to be more of a curving motion, because think about it. The ball is not going to hover for 0.3 seconds without any movement at all. There's probably supposed to be a little bump or arc in between these. So what we want to do is go ahead and kind of curve it, go up a little bit more, and then back, down, and stop. And you don't actually want to extend or do an arrow because Jenna caught the ball, so it stopped moving, and we stopped our timer. Okay? And so one more time, I do want to give ourselves a little note that we want to connect because it's continuous. Connect because continuous. And again, these are little notes so that when you go back and think, well, why is this one connected and why isn't this one, that you actually do have a note now that tells you why. And then there you go. We have now analyzed our second scenario. So you would need to be able to, hypothetically, do this all on your own. Okay? Read the scenario, determine the independent and dependent variables, write the dependency statement, determine if it's continuous or discrete, then write the domain and range based on that fact, and lastly, graph it, again, independent and dependent, scale, and do you connect it or not? Okay? It seems like a lot, but I promise that's what we're going to focus on our next class, and it will seem more manageable. All right. Thank you, guys. See you next class.